the staff with the scientist from Google to give us the talk about his recent works on the nanospheres applied to the quantum chemistry applications. Yes.
Okay, thanks for the introduction. So companies around the world, startups and big corporations are pouring billions of dollars into building quantum computers. And on many of their websites, you'll see a roadmap that kind of resembles this. You have a few physical qubits today, maybe 100. And then 5 or 10 years in the future, you have many, maybe 1,000,000. So at the top of the mind of the people who run these companies are, when will I see my return on investment? When will these quantum computers actually solve something that is useful? So the scale of these problems that can generate commercial value, that's what we call utility scale. And really what everybody wants to know is where along the line of these roadmaps can we solve a utility scale problem? Usually there's some translation to logical qubits. These numbers are physical qubits, like how many superconducting qubits you have, how many ions do you have in your trap. But physical qubits are too noisy to solve the utility scale problems that we believe that these will be useful for. To do any of that, we need quantum error correction, and that means there's going to be some overhead in translating the number of physical qubits you have to the number of logical qubits. And just to kind of give a rule of thumb, roughly speaking, you'll get 1 logical qubit for every 1,000 physical qubits. So in the long run, in 10 years, the machines that people expect to build would host maybe 1,000 logical qubits. So that's a kind of utility scale application that we would like to have, at most 1,000, but much more preferably if much fewer than 1,000. So there are many possible types of applications that one could call utility scale, but the ones that we consider clearest in generating useful commercial value would be for solving electronic structure problems. So these are things involving electrons, which are fermions, electrons interacting with nuclei and so on, either in a molecule or in a material. Today we are in the NISQ or MISQ era, so we are still operating on physical qubits. And we look at near-term applications that maybe might not use more than 200 physical qubits. And the number of gates you can apply there are very much limited to either the physical error rate or to very small error correcting codes. So these are toy examples. They are in no way utility scale. They serve as ways to benchmark progress and maybe to test early ideas, but they are still not yet at the level of generating value. Where value starts to show up is when you start to go to the regime of at least 100 logical qubits and maybe 1 billion quantum gates. So these are problems that definitely need full quantum error correction, the scale of 1,000 physical qubits per logical qubits. But at this scale, it is quite clear what the problems are to solve and how fast we can solve them on these proposed devices. Generally speaking, these electronic structure problems will be ab initio simulations. So you have some first principles representation of a molecule or material, and then you now simulate it on your quantum computer, such as by Hamiltonian simulation or phase estimation. And there's a lot of interest in bringing down the number of gates needed and the number of logical qubits needed to solve all of these in a timely way. The sooner you can solve these, the more valuable quantum computing will be, and the more jobs there will be for all of us. So that's a goal. When we choose what are good utility scale problems, it's also important that these problems are not too easy to solve classically. Because if you could solve them classically, you wouldn't have a need for a quantum computer. So you need to thread the line of it needs to be useful, it needs to be classically hard, it also needs to be quantumly easy. There are not too many problems that fit all of these criteria, but for the case of chemistry, where you have some number of orbitals n, so this is an active space representation. Generally speaking, there's the consensus that at greater than n equals to 50, and this is orbital, so that translates to 100 spin orbitals, and each spin orbital maps to a qubit. At around this scale, it is more or less unambiguous that the best classical methods, such as DMRG and so on, will fail to give you the accurate solutions you need for quantitative predictions. So the accuracy you need is what we call chemical accuracy. This is 1 kcal per mole or 1 millihartree. And this is derived from the Arrhenius rate equation. This is the accuracy you need to, at room temperature, estimate reaction rates to, say, a factor of 10. Obviously, you like it if you could do better with a factor of 10. So this is kind of like the start. We want to look at how many quantum gates we need, how many logical qubits we need to solve problems on the scale of 50 orbitals, estimate the ground state energy to chemical accuracy. And there are quite a few benchmark molecules that have been studied that fall into this class. For instance, if you want to look at catalysis, like nitrogen fixation, which is how you convert the nitrogen in the atmosphere into fertilizer, there's a catalyst that's based on an iron compound, FeMoco. And then there are many others, like for carbon capture and for discovering drugs. All of these are based on some kind of catalyst, and we would like to simulate the ground state energy of these catalysts in various configurations. So a true commercial scale application of these would require you to run each simulation hundreds of thousands of times. Here we are just looking at the start. How much would it cost to run one simulation, one configuration, and get one energy to chemical accuracy? And over the course of the past several years, you can see that there has been pretty rapid progress. If you were to plot this on this log linear plot, it seems like we have exponential speedups just due to progress in algorithms. The first major serious estimate for FeMoco in 2017 said that on a reasonable machine, you would need a century of runtime just to get one energy. But every few years, you have a factor of 10, a factor of 5 improvement. And these improvements have a great way of compounding. Until today, it seems plausible that you could solve one of these problems in maybe an order of hours. So that's pretty great. Maybe if you extrapolate, perhaps you could get even faster in the future. But it's also important to note that every next factor of 5 becomes harder and harder to achieve. At some point, we will plateau. But, there is still hope that we could bring these numbers further down. So today in this talk, I will focus on 2 papers that we've had from Google about the techniques that we use to achieve this most recent set of results. How in year 2005, we can simulate n equals to 54 in the matter of hours and n equals to 76 in the order of a day. So before we go into the details of all that, it's good to very clearly define the problem that we are solving. So we are going to estimate these energies by quantum phase estimation. This is considered the scalable approach to solve these problems. So unlike, for instance, variational approaches, quantum phase estimation comes with provable error guarantees on how many queries you need to get some target precision. There's no like heuristic hand waviness involved here. It's a very clear algorithm depending on, of course, that depends very clearly on like parameters like error and so on. So you have a Hamiltonian, there's a bunch of eigenstates. You want to get the energy of the ground state, so that's k equals to 0. And you have as an input a child wave function that has good overlap with the true ground state. So we know that in general, it can be, this assumption is not going to hold. Finding the ground state of an arbitrary Hamiltonian is in the class of problems that we call QMA hard. That means that it could take exponential time. And this exponential time shows up in how the overlap of your trial state with the true ground state could be exponentially small. But it turns out that for this class of electronic structure benchmarks, these active space problems, there's strong empirical evidence suggesting that you can actually make these good trial states. And how it works is that if you have a good DMRG ansatz for your ground state, even though your DMRG solution could be off in energy, it could actually have pretty good overlap with the true ground state. So this is not provable. This is just what we have observed empirically. The details can be found in this PIX quantum paper. And so we'll just go along with that assumption. There is, as a promise, an input state with good overlap to the true ground state. So now the cost of running these algorithms and getting the energy to chemical accuracy is more or less just a cost of phase estimation. And you would multiply this by 1 over the square root of this probability, but we take that to be 1. So here we benchmark algorithms rather than our ability to prepare the ground state. So now that you have this input, the next step is to apply phase estimation. That means that you're estimating the phase of something. So we apply our phase on this ground state by some kind of unitary quantum circuit that applies a phase f of h on your input state. So what this function f of h is depends on your Hamiltonian simulation algorithm. So like if you want to do real-time evolution, f of h is just h, linear in h. But if you're to use a quantum walk to apply this phase evolution, f of h would be something slightly different. Similar but different would be the arc sine of h. The arc sine of h is kind of linear when h is 0, so that's kind of similar to time evolution. The point is that you want to have some mechanism to accumulate the phase on the ground state. That is step 3. If you apply this u multiple times onto your initial state, then the ground state will accumulate the phase. And when this phase gets bigger and bigger, there's a way to estimate what this phase is by various flavors of phase estimation algorithms. And we understand very well the complexity of estimating this phase to any desired accuracy epsilon. The scaling is going to be given by that there. That's going to be 1 over epsilon. So this is called the Heisenberg scaling. And then it's going to be multiplied by the gradient of f of h. So in time evolution, this is just linear. So the derivative of f is 1. In the case of the quantum walk, the derivative of this arc sine is a bit more complicated. And that will turn out to be very important to get speed ups by the techniques we show later. So the overall cost of our algorithm, now throwing in some constant factors like this pi over 2, is going to be given by this expression up here. There's going to be pi over 2 times 1 over epsilon, then multiplied by a certain normalization parameter lambda. This you can think of as like the inverse step size of your simulation. If you need like a very small step size, you have to pay a large cost. But if you can make do with a very large step size, you can make do with a smaller cost. So if you were to directly differentiate this arc sine function from the previous slide, you'll find out that this lambda effective is going to be this strange looking function. There's this normalization factor lambda. I'll go into that later. It has to do with the normalization in the block encoding representation of your Hamiltonian. And then that's going to be the energy that you're trying to estimate. So roughly speaking, in prior work, there wasn't really a way to tune E. More or less, in general cases, E would be around 0. And so lambda effective is just a square root of lambda squared. So it's linear scaling in this block encoding normalization. So overall cost is pi over 2 epsilon multiplied by the number of queries you need to make to this block encoding, which is 1 per quantum walk. And then multiplied by the number of quantum gates you need to block encode this block encoding unitary. I'll talk a bit more about how you make this later. And there are 3 parts to this talk. The first part, spectrum amplification, is the observation that the arc sine function is very nonlinear. This means that if your energy, by coincidence, happens to be close to the edges plus minus 1, or in the language of the lambdas plus minus lambda, there's enhanced sensitivity. A small change in the energy will lead to a big change in the arc sine. So you can exploit this enhanced sensitivity to estimate phases faster. You can use a cost precision setting for phase estimation, but this cost precision will be shrunk into a very fine energy error because of the arc sine function. So part 1 is about spectrum amplification, the case where if E by coincidence happens to be close to the edges of this. But this is not a generic feature that will hold for any Hamiltonian. You have to put in a lot of work to make that happen. So to make that happen, that is part 2. This is a sum of squares representation. How you can optimize a certain representation of a Hamiltonian to actually engineer this close to the edges behavior to get your spectrum amplification. So this is still quite generic. In part 3, we'll apply this to the electronic structure problem, and then we show some electronic structure specific optimizations that allow us to optimize all of these parameters like lambda, the closeness of E to lambda, and the cost of the block encoding simultaneously to get the overall improvements that I plotted versus time in years. Okay, So before we go into the details, it's good to go over some preliminaries. So a very common model for how we represent matrix problems on a quantum computer, and the Hamiltonian is kind of very big matrix, is through the block encoding framework. So the block encoding is a unitary circuit that is defined to have the matrix you want in the top left block. And then because unitaries are normalized by at most one, there must be some normalization factor lambda that is at least a spectral norm of H. In general, lambda could be a lot bigger than the spectral norm. This depends on the detail of how you implement your block encoding circuit. If you apply this block encoding onto your system space and an ancillar register, being in the top left block means that if you're to look at the output, condition on the 0 state in the ancillar register, you have applied your matrix over lambda on the quantum state. So this is a definition. There are 101 ways to block encode all sorts of different matrices. A very prototypical example is called linear combination of unitaries, and you'll see this a lot in the block encoding literature. It's based on the idea of 3 quantum circuits. The first is a select circuit. So this is a controlled circuit where controlled on an index J, you apply the Jth unitary. There's a preparation circuit. This acts on the ancillar register, where it acts on the 0 state to prepare a superposition state over the indices J, where the coefficients are the coefficients of the different U's that you want to take the linear combination of. And it turns out that if you were to combine these circuit elements, prepare select, prepare inverse, you have a recipe to block encode a linear combination of unitaries. And the normalization factor lambda is going to be the L1 norm of the coefficients. So this is what we'll use in a lot of our constructions. It's good to know. And the dominant cause of these is usually in the prepare component. It turns out that, for instance, in electronic structure, you have to prepare a state over, for instance, let's say just hand wave n cubed terms. So this will have a gate cost of n cubed. And there are many ways to create the quantum circuit that prepares this state. It will always take n cubed gates, but then there are ways to do a trade-off between Toffoli count and qubit count. Toffoli gates are kind of like the expensive gates in a quantum error corrected model. Everything else is considered cheap. So it's good to minimize the Toffoli count. And if you're to use additional ancillar qubits to assist this state preparation, you can reduce the Toffoli count by a linear factor. So multiply the ancillar qubits by a factor lambda, Toffoli count goes down by a factor lambda. This is something that we will use quite extensively. It's good to know about. So now that we have the block encoding, how do we convert it to the quantum walk? How do we make this arc-signed phase evolution? So the answer turns out to be pretty simple. Take your block encoding and now apply a reflection on the ancillar register. The proof to do this can be found in all sorts of papers, but all you need to take away from this is that this nice trick will give you your nonlinear phase evolution, converting the Hamiltonian and the block encoding to a phase of the overall quantum circuit. Another useful trick is called quantum singular value transformations. If you were to interleave these block encodings with partial reflections parameterized by some angle phi, you can, instead of block encoding H, you can block encode any polynomial of H. And if you want to block encode like a degree K polynomial, it suffices to make K queries to the block encoding. So we'll use this later on as well. So now how do we engineer this block encoding where the ground state energy happens to be close to lambda? So one intuition here is to simulate the so-called square root of the Hamiltonian. Suppose, and this is like a pretty strong supposition, suppose that you could represent H as a sum of squares. Usually we think of H as a linear combination of terms. Like earlier I said, H is a linear combination of unitaries. Let's now consider H being a linear combination of squares, a sum of squares. It so happens that if H is a sum of squares, you can define a certain Hamiltonian square root of this Hamiltonian. It is not a Hermitian matrix, it's a rectangular matrix. You can define this, and what's nice about it is that if you square it, you recover the original Hamiltonian. And what's cool about this square root here is that if you think about the singular values of the square root, they are going to be the square root of the singular values of the original h. So if your singular values of h initially were less than 1, when you square root them, they become bigger. 0.01 becomes 0.1. This is the stretching that I was talking earlier about, like this arcsine nonlinearity. So the intuition is that if you could simulate the square root, you stretch the spectrum by a square root factor. And if you were to hand wave, this sounds like maybe you could, get this square root amplification in the sensitivity of phase estimation. So this is easy to say, but how would you actually simulate the square root? Because Hamiltonian simulation is for Hamiltonians, and Hamiltonians are Hermitian matrices. So how do we do this? So this has been studied before, and there is a pretty well-established way to do this. So one way to do it is to start from the block encoding of this square root function. So here I have, this h square root. It's non-Hermitian. I've defined it as the cat j tensor with the operator oj. And just like how earlier there was this LCU construction to block encode a linear combination of unitaries, it turns out that you can kind of take half of an LCU construction to block encode this rectangular matrix. So you can do it. This is 7 and 8 is how you do it. Then now, given this ingredient, the block encoding of the square root, there's a way to define a Hermitian matrix, that's square root h, which satisfies this property of being a square root of the original h. This Hermitian dilation is a Hermitian matrix. So if you can block encode square root h, you can apply qubitization to make a quantum walk. You can plug in the phase estimation, and that's all done. So this is how you could do it in principle. But it turns out that you could do slightly better by a factor of 2. And a factor of 2 doesn't sound by much, but we are now in a regime where every factor of 2 improvement you get is like, a factor of 2 improvement, and where investors get their money back. So asymptotically, it doesn't sound great, but practically speaking, today, all of these factors of 1 and 1.5 and 2 and 3, wherever you can find them, these are extremely valuable. So a trick that we use in this paper is a way to simulate the Hamiltonian square root 2 times faster. And it's a pretty simple trick. So earlier I talked about singular value transformations, how you can apply any degree k polynomial to your block encoded matrix. So here, just apply the polynomial that's 2x squared minus 1. This is the Chebyshev polynomial of degree 2. So if you do this, you get a very cool looking block encoding of your original Hamiltonian. You can see that there's this h, but some interesting things have started to pop out. You now have this shift by -1. You also have this shift by beta. And these constant shifts will be key to engineering the ground state energy being close to the edges of the arcsine function. So to recap, we have the sum of squares representation. From that, we can define a square root. From the square root, we can use QSV2 to define this shifted Hamiltonian that we will see later has been engineered to be close to the edges of the arcsine nonlinearity. That's how we will get our square root speed up and the effective lambda for phase estimation. So if we were to apply qubitization to this block encoding and make it a quantum walk, now the phase evolution that you apply on your initial state, f of h, is going to be arcsine of this, this shifted Hamiltonian. Previously, without any of these tricks, it would be the choice at the bottom, just arcsine of h over lambda. But now you have all sorts of identity shifts. So if you plug this f of h into this formula, telling you how many queries you need for phase estimation, you'll see that now lambda effective has this square root dependence, that's this 2 multiplied by the block encoding normalization lambda, but now multiplied by this strange looking quantity, the ground state energy minus beta. So beta is going to be a certain energy gap that you would like to make as close to the ground state energy as possible. So that's the non-trivial part. How do you actually make beta close to the ground state energy? Generically, beta can be all over the place, but later on we'll want to make beta close to the ground state energy. And because if you can do that, if E minus beta is much less than lambda, then you'll have your advantage over the previous case of phase estimation where you didn't use any of these spectrum amplification tricks. Any questions so far?
Yeah, I have a question. So do you have any constraint on Hamiltonian that, like at any point of time in the evolution, the energy has to be strictly positive?
The short answer is no. You can always find a sum of squares representation with an appropriate beta. And later on, I'll talk about how actually there are ways to make beta arbitrarily close to E, but there's a price you have to pay that makes us not want to do that. So at a high level, you have this square root improvement from scaling with lambda to scaling with square root lambda times square root delta. For the case of phase estimation where your ground state overlap is 1, the cost is just going to be pi over 2 epsilon times lambda effective. In our paper, we also consider the more general case where the overlap with the ground state is some arbitrarily small number. So maybe this could be the case where you're dealing with a harder problem, something that's maybe closer to QMA hard. So in that case, there are questions about what would be the asymptotic complexity of estimating the ground state energy to some desired epsilon, in this case of finite overlap. So using the non-spectrum amplified algorithms, you would have this lambda scaling. But now using this spectrum amplified result, you can get square root lambda times square root gap. And then you can also get something similar for time evolution. So this here is good to know. It's like, here's the asymptotic complexity, but that's it's just good to know. It's not what we'll talk about in the rest of the presentation. So now we go on to sum of squares. How do we actually compute these nice representations that have beta close to E? So we have H, it is a sum of squares. You want to minimize this gap. That's the difference between the ground state energy and beta. And for any beta that you might compute, this is a lower bound on the true ground state energy because OJ dagger OJ is positive. So that means that its lowest energy must be at least 0. So that means that beta is a lower bound on the ground state energy. So this is quite cool. Usually when we think of variational approaches to getting energies like in VQE, this is about variationally finding an upper bound. And then, there's like 10,000 papers on that. This here comes from the opposite direction. It's about finding a lower bound on the energy. And what's very interesting about these lower bounds is that they translate into speedups for quantum algorithms for finding the energy. So this is a way to incorporate prior knowledge of your quantum problem into the quantum algorithm. And then that's usually not so easy to do. So how do we go about getting good lower bounds on the ground state energy? How do we make beta big? So the first step is to define a basis that these operators OJ are spanned by. So for instance, you can think about Pauli operators. You have XYZ. You could think of monomers of Pauli operators, multi-monomers like XYZ multiplied together, XXX or ZZZ, or all the different possible combinations of Pauli operators. So you can define an order for the basis that will be supporting these operators. Maybe you just want to consider products of 2 Pauli operators. Or maybe you want to consider products of 3 Pauli operators. Then it turns out that as you increase the order, like as you add more and more Pauli operators that are spanned by these O's, you can find a beta that gets closer and closer to the ground state energy. And in the limit where O's is spanned by all possible Pauli operators, you can actually recover the ground state energy exactly. But this is not free because as the basis of your O's increases, the number of O's increases and the number of coefficients that each O takes a linear combination over the basis increases. So in other words, the amount of data you need to represent this huge sum of squares increases. So the classical approach, you can frame this optimization of beta as a semi-definite program. This semi-definite program will optimize over all possible ways to take linear combinations of this basis. And the complexity will scale very rapidly with the degree of your basis. So for instance, if you have n qubits, and then you restrict yourself to Pauli operators of products of k of them. This is going to be Pauli n to the k time. So of course you could get the true ground state energy if you were to choose k to be the size of your system. N to the n time is pretty bad. So that's the price you pay. You can find a sum of squares representation. You can define a sum of squares representation that would be really good, but you can't actually compute it. And moreover, if you want to actually implement the block encoding of the sum of squares, this depends very sensitively on the number of terms. So you have to balance the factor of better gap means better lambda, but if the block encoding cost exceeds the improvement in the gap, you've lost. So there's some balance where you want a small order combined with a reasonable improvement of your gap. And now we talk about the application of this to electronic structure.
Sorry, can I ask another question?
Yeah.
So in the previous slide, the fourth point, you wouldn't have this problem if you use a quantum STP solver. You should get much better.
That is so I do not know the results for quantum STP solving. Maybe it's plausible that you could get beta faster, but we also know that estimating the ground state energy is, in the worst case, like QMA hard. So there must be some kind of no-go theorem telling you the cost of estimating beta as beta goes to EGS. So maybe for some cases it could be cheap. In the worst cases, even if a quantum STP solver would still have exponential costs. But focusing on the cheap cases, it is informative to know that you can get a good beta. But at the end of the day, you still need to block and code your quantum sum of squares. So this means that your quantum STP solver must also output a description of all the O's. And if you just think about how many bits of data you must read out from your quantum STP solver, that is still going to be Pauli n to the k. So you might get beta faster, but you can't output the full solution faster.
Do we know the scaling of the gap between beta k and ground state energy with k?
It's very problem dependent.
It probably depends on the gap of the Hamiltonian.
Yeah, it depends on a lot of different things. But one intuition you can develop for this is, what is the order k you need to reproduce order k perturbation theory? So it turns out that degree k equals to 3 for some generic instance of electronic structure can reproduce third order perturbation theory. Degree 2 is like second order perturbation theory. So maybe nobody has done this analysis, but maybe you could extrapolate and say an SOS of order k will reproduce order k perturbation theory. And then how good perturbation theory is at approximating your ground state, that's like very problem dependent. Okay, so now for electronic structure. Previously, I kind of talked about Pauli operators. Now we talk about fermionic operators. So the first equation I have here is what most electronic structure problems that people want to solve will look like. They will be number conserving. There will be n orbitals. So there are 2 n spin orbitals. That's the index Q. There will be a one body term. These are the hopping terms AP dagger AQ, usually representing something about like kinetic energy and interactions of electrons with nuclei. And then there will be the difficult part, which are the electron-electron interactions. So these interactions are represented by a huge tensor of size n to the 4. It's a huge number of terms that would be very expensive to block and code, but we must live with that. And if you have never seen fermionic operators before, you can just understand them as being mutually anti-commuting Pauli operators. Each fermionic operator is a linear combination of 2 Majorana operators, and the Majorana operators are defined to mutually anti-commute. This is a property that you can represent with just Pauli operators. So if you know nothing about fermions, just think about Paulis. What Paulis anti-commute? XYZ. And then now if you have many different n qubits, what are the Pauli operators on n qubits that mutually commute. Any set of them that mutually commute defines your Majorana operators. So this is good to know because it is also how we will encode fermionic problems onto qubit quantum computers. It's all through this fermion to Majorana to Pauli representation. So to understand good ways to block encode is good enough to understand, how do you block encode sums of Pauli operators that mutually commute. So for these benchmarks earlier on, they're actually slightly simpler than this most general form. They are Hamiltonians that you obtain from applying non-relativistic quantum mechanics. So in that case, there's an additional index here, the spin. I didn't write the spin here. Oh, I wrote the spin here. There's an additional dependence on the spin that shows up in the general case that doesn't show up in the spin-free case. So here, instead of PQ summing over 2n things, it's just sum over n things. And the interaction, this hopping term, this composite EPQ object, symmetrically sums over the spin 0 and spin 1 parts. This is a problem definition. You don't really need to know more about it in the following. It's something that simplifies the number of terms you need to define in your 2-electron interaction tensor. So now in the context of the finding a good sum of squares, you want to minimize lambda effective. That's lambda square root times lambda gap times the cost of each block encoding, such that your sum of squares reproduces your original Hamiltonian. So how you might go about doing this, if you were to follow a recipe, is at first you choose a many-body order. The most general degree 2 order is all possible products of 2 fermionic operators. So that looks like that. You could of course choose higher degree, like degree 3 or 4 and so on. You get better betas, but that doesn't necessarily mean that you get advantage because you have more terms and you have more costs. So you can't choose k to be too large. You want k to be small enough to get advantage. The second problem that is faced here is that although I earlier said that you could find the optimal beta for any fixed k by an SDP, which is polynomial time, the SDP only optimizes for beta. There isn't any kind of regularization that will try to make lambda or the block encoding cost small. And indeed, when we did numerics on running this SDP, we found out that although the betas are good, the lambdas could be just terrible. So basically, how do you overcome these two problems? So the first problem is mitigated by doing some numerics and finding out that sure, degree 2 is the most general. You have this most general degree 2 basis for your operators. It has a certain good beta, but has a pretty large amount of data. There is a subset of the degree 2 operators that still spans the Hamiltonian that we are interested in, this spin-free representation, and that's to choose this so-called spin-free subset of the degree 2 operators. So because this is a subset of the general case, you have a worse beta, but it turns out that it strikes a nice balance between the amount of data you need and having a good delta. I don't have the data for the general case, but for this spin-free case in our paper, we show that the gaps you get, and you can think about these as the estimates for the ground state energy, lower bounds, they are not good enough to give you chemical accuracy. So this is in no ways a numerical approach you use to solve your Hamiltonian classically. But the gaps, here E gap is on the order of 1 Ha3, 3 Ha3. This is still going to be small compared to lambda. So as our cost is square root of lambda times the square root of gap, in our paper, we validated that this spin-free subset is good enough to get your advantage in spectrum amplification. It's a big question about whether you can add a bit more to this spin-free generating set. Maybe you have to add the most general generating set. Maybe you can just add a little bit more. You get slightly better betas, but your block encoding cost goes up. There is a lot of room to optimize these results. Here we just show that the spin-free case is good enough to get these constant factor speedups. You could do better, but that's future work. And I focus a lot on constant factor improvements. There's also interest in understanding whether this idea of spectrum amplification has an asymptotic improvement. Like all of these examples that I showed you, they're on a finite number of orbitals, like 20, 30, 40. It'll be more convincing that spectral amplification is general purpose in combination with sum of squares if you could, show that there are generic quantum systems where you can asymptotically prove an advantage. Like as the system size grows bigger and bigger, you always get some, improvement in the exponent of your problem. So the such that Yi-Kitaev model is a famous toy model to understand the behavior of strongly correlated materials. It's a toy model, so it doesn't like capture all strongly correlated materials, and it's you shouldn't like extrapolate the insights you get from it too broadly. But we are able to show that even accounting for of these block encoding costs and whatnot, there are good sum of squares representations that unambiguously give you an n to the 1/2 speed up over not using sum of squares. So that's nice. It's just a bit of evidence showing that this can have generic utility, beyond just the specific examples that I show here today. And then, where else this might apply, that's interesting future directions.
May I know, so for here, for the SOS, which degree you choose? Is it
This is degree 2.
Yes, because I remember like from Hastings' result, he argues like for the SYK model you need 6 degree SOS to approximate with the perturbation precision.
Yeah, so Matt Hastings' results are like what I said earlier. What is the degree you need to to reproduce perturbation theory to that order? So, like you say, degree 3 is needed for perturbation to degree 3. But it turns out that degree 2, even though it only reproduces perturbation theory to degree 2, it still gives you enough of an improvement in the gap to achieve this claim. And what's more, even though degree 3 would get you a better gap, you would go from n to the 4 terms to n to the 6 terms. So that could very well totally wipe out this tiny n square root n improvement here. So once again, you need to carefully balance the size of your representation with the improvement in the gap. Okay, so now let's go on to the more nitty-gritty details of how we applied this to speed up chemistry and what other improvements we made in simulating chemistry in general. So the main claim in our paper was this improvement in Toffoli gate counts over time. So in the earlier slide, I showed you this improvement in Toffoli count versus years. And each of these improvements usually come with some new insight about how to better simulate electronic structure. So the very first estimate in 2017, that's also like the very first serious estimate. Back then, quantum algorithms weren't quite as mature, so people use trotterization. It's very old-fashioned, but maybe it doesn't scale quite as well. Then later on, you had inventions like qubitization, and then you also had ways to compress this 2-electron tensor of n to the 4 terms into smaller and smaller low-rank approximations. There's a single factorized approximation, there's double factorized approximation, there's THC. And then later on, there were also ways to reduce lambda by a technique called symmetry compression. So in this work, we have a new low-rank representation for this 2-electron interaction. It's a generalization of DF and THC, so we creatively called it DF-THC. Then we also apply spectrum amplification, as described earlier on, combined with symmetry compression from 2014 and 2015. So overall, the number of qubits that you need is still on the order of 1,000. So this could kind of fit into the late game milestone 6 1 million physical qubit device. That's nice. We would like to bring this number down. And the number of Toffoli gates compared to previous work has also gone down. So we would like this to go down further. But for today, this is what we achieved.
So here, what's the exact task? Is it the dynamics or the ground state or the energy?
Ground state energy. We want to estimate the ground state energy to 1 millihartree. So the epsilon in phase estimation is 1 millihartree, and then the thing in the numerator, the lambda, that will turn out to be on the of tens or hundreds of Hartree. So that's kind of like the scale.
Is it possible to use like the randomized LCU like to for this task? I mean, although there'll be several iterations, but since the story types will be quite shorter, is it possible to benefit from like this kind of technique?
So there are challenges to that. The first challenge is that you have worse scaling. So these methods will go as 1 over epsilon squared scaling.
Yes.
So when epsilon is already like 10 to the power minus 3, squaring that would make your runtime larger by a factor of 1,000. So your 1 day simulation will become a 1,000 day simulation. There are ways to trade off between depth and time. Like you don't have to use the minimum depth 1 over epsilon squared algorithm. You can run like, maybe instead of phase estimation to 1 millihartree, you could run it to 1 hartree, and then you could repeat that. So that would increase your overall runtime by some large factor, but not as large as 1,000. You could use a shallower circuit by a factor of 1,000. But the problem here is that now whether you actually get your ground state energy in the end depends very much on the overlap of your initial trial state. Phase estimation has a very nice feature of no matter how bad your trial state is, so long as it has some finite overlap, the energy that you get at the end will, to your desired epsilon, be accurate. It will be the true ground state energy plus minus epsilon. When you use these low depth approaches, you now will have a bias estimate. It'll be plus minus epsilon, but plus minus epsilon of what? Unless your trial state happens to be very close to the true ground state, it'll be plus minus about some uncontrollable shift from the true ground state energy. So these depth time trade-offs are possible, but you need to use them carefully. And generally speaking, we target the long term. So we are interested in, at the scale of these large machines, when can you unambiguously get utility scale? So it's possible you could get to utility scale using the approaches you described, but there's going to be a very high price in time because you have worse scaling. And also you no longer have a guarantee that your quantum computer is outputting the correct answer.
Yeah, thanks.
All right, so the interactions between the electrons in a molecule, they are governed by the 2-electron interaction tensor. So that's this in the top right, I call that H. In the top left, that's V, because we've reordered the terms. You can represent these interactions with tensor network diagrams. So the Coulomb operator, if you just look at it at face value, it would be a tensor with 4 legs. Each leg is of bond dimension n. So this overall thing has n to the 4 terms. If you to block and code this, you would need to prepare a superposition state over n to the 4 coefficients. And that's a lot of coefficients. We would like to cut that down. But it turns out that this interaction is actually very structured. The tensor matrix elements here, they are derived from integrating some basis functions with respect to the Coulomb operator, 1 over Ri minus Rj. And the Coulomb operator is actually a low rank operator. Like you can see this by taking the Fourier transform of 1 over R. It's low rank and it's also positive. So this means that any tensor, HPQRS, that you compute that uses the Coulomb kernel will inherit some of this low rank behavior. So what this means is that instead of having n to the 4 terms, you could actually represent this tensor with n to the 4 terms using fewer than n to the 4 bits of information. So the analogy here is that if you have n by n matrix, if you do, as n squared elements, but if it is low rank, maybe it could be represented by as few as just n elements, a single eigenvector. So a similar analogy here holds for these higher order tensors. There is theoretical and empirical evidence showing that these n to the 4 terms, this high order tensor, can be factorized into much fewer terms. And how we understand these factorizations is through these tensor network diagrams. the first attempt at finding low-rank factorizations was called single factorization, and this is done just by splitting your V tensor into two parts, H on the left and H on the right. And even though there are still 4 bonds going out of dimension n, it turns out that the rate bond, it turns out that it's good enough to choose this to also be of bond dimension order n. So now instead of one tensor with n to the 4 elements, you have 2 tensors with n cubed elements. So that's an improvement from n to the 4 to n cubed. And you can understand this just by looking at the dimension of the bonds and how many tensors you need. There isn't a unique way to decompose these tensors. Whatever you can dream of, you can try to plug in here. And so the next dream that people had was to perform a eigen decomposition of each of these stacked H tensors. So you get this strange looking tensor network diagram. The blue lines are going to be of order n. The red lines are going to be of order n. There isn't actually an advantage in terms of the information density, but for technical reasons, double factorization has a smaller block encoding normalization. Then in 2021, somebody dreamed of a different way to factorize these tensor diagrams. That's tensor hypercontraction. It looks like that. The blue lines are all the same bond dimension. They are order n. And if you kind of stare at these, you'll see that the natural generalization is to just overlap all of them, and you get double factorized tensor hypercontraction. And here we choose the blue, red, and teal bonds to all be free parameters. The bond dimension are things that we scan over to get the most compact possible representation of your original 2-electron tensor. And this representation is nice because it turns out that it compresses information even more by some constant factors, and you also improve the normalization factor by some constant factor. But now if you combine it with this sum of squares spectrum amplification, you get a speed up. So I've talked a lot about tensor factorizations, but how are these related to sum of squares? Well, it turns out that this mirror symmetry that you see in all of these tensor diagrams, if you split it down vertically, this mirror symmetry means that every one of these tensor factorizations is a sum of squares. That's a cool thing. By optimizing these tensor factorizations, you can optimize them such that you have a way to tune for this beta. You have a way to tune this gap because that's a natural property of tensor networks with this mirror symmetry. Like at the top right, I have the original representation. At the bottom right, I have the same thing but represented as a sum of squares. So there you go, that's a sum of squares. It's done. To go into more detail about what are the choices of bond dimensions that would make a good factorization. So there isn't really like a unique best way to do it. We've tried a lot of different combinations of bond dimensions, but roughly speaking, we found that it's good enough to choose the rate bonds to be bond dimension order 1 and everything else to be bond dimension order n. And moreover, when we find these factorizations, we do not require them to exactly reproduce the 2-electron interactions. We only need them to reproduce it to some finite error. In this case, the error is going to be 1 millihartry. And what's nice about understanding the bond dimensions here is that they translate in a very direct way to the block encoding cost. The block encoding cost is going to scale the number of terms, and these bonds tell you precisely how many terms there are in the block encoding. So there are going to be table lookups and state preparations for each of these tensors, and they scale in a very straightforward way with the size of the tensors, which is in turn given by the bonds. This is a technical ingredient that we use to reduce lambda as well. It turns out that there is the initial electronic structure Hamiltonian H, but there is an equivalence class between many of them. This is because the ground state that we are looking for is known beforehand to obey certain symmetries. Like we know beforehand how many particles are inside. We know beforehand what is the spin of the wave function. So all of these symmetries mean that there is an operator, like the total particle number operator or the total spin operator, that if you were to subtract it from this a priori known symmetry, will annihilate this quantum state. So what this means is that your Hamiltonian that you use for electronic structure is equivalent to any Hamiltonian that is this annihilator multiplied by an arbitrary operator. So really, when we find good sum of squares representations, you are finding the best betas and lambdas with respect to a continuous space of equivalent Hamiltonians that are given by these symmetry shifts. So this is just a variational freedom that we have to find good solutions. And it turns out that this is very important in reducing lambda, because the lambda for a given Hamiltonian, just by definition, is going to be worse than the lambda over all possible Hamiltonians. This will generally give you a factor of 5 improvement. So it's important to use when you want to get good resource estimates. And what's nice about the SDP approach to solving the sum of squares is that you have a guaranteed polynomial time classical algorithm to get the best beta. Unfortunately, it doesn't regularize for lambda and all the other things that you might care about in the overall course of the simulation. So what we do here is very naive. It's very straightforward. Let's just define a cost function that attempts to simultaneously minimize all of this. The first term here is going to be the error between your DF-THC factorization with this continuous space of symmetry shifted Hamiltonians. You want to minimize the error between the two. In optimizer, we just take the Frobenius error. There's an additional term from the lambda. You want to minimize that as well. And then you also want to minimize the gap. So that's like E gap. And in all of these nonlinear optimization problems, usually there's a lot of black magic involved. You need to pick good regularization parameters, like how much weight you apply to minimizing the norm versus minimizing the error versus minimizing the gap. So we did a study of this. You can find the details in our paper. And so we have kind of good regularization parameters that finds solutions effectively. And the key point here is that this is nonlinear optimization. Finding the optimal solution in the worst case will take exponential time. But that's not a game breaker, because you don't need the best solution. We don't need the optimal solution. We need a good solution. And it turns out that just empirically, if you're to randomly initialize all of these tensors, you can find by gradient descent good solutions really, really fast. So we implemented this here on GPUs, and it finds good solutions for these big examples in the order of minutes. In the past, there was some question about, sure, you have these very cool, fancy factorizations, but if the classical cost of finding the factorization is more expensive than the quantum cost of running your machine, there's no point doing that. But here, you kind of just say that, yeah, that's a non-issue. You can find these factorizations easy. So this is a practical approach that we have no theoretical guarantees work, but like machine learning, it works, and we validated the solution to work well enough, and it works for everything that we tried it on. So this solves problem 2. How do you jointly optimize for the gap, the lambda, and the block encoding costs all at the same time? So early on, I talked about the LCU approach to block encoding these things. That's going to be a select and a prepare. For the double factorized tensor per contracted representation is the same thing, but just with more terms, bigger coefficients, bigger selects. It's the same story told in a different way. And what the main takeaway message here is that we've been able to compress the amount of data needed in the 2-electron tensor so much that actually this preparation routine, encoding the coefficients, is no longer the dominant cost. The dominant cost is actually now in this select operation, which previously wasn't the case. So if you want to improve costs further, that's what you would try to target. Generally speaking, when we optimize algorithms and resource estimates, you always want to find the bottlenecks. The bottlenecks will tell you what to focus your attention on. And so this tells us what to do next. This is in the regime of like 1,000 logical qubits. There are ways to compile a circuit into fewer logical qubits. In those regimes, different parts might dominate, and so you redo this analysis. So at the end of the day, we can make this nice plot. If you were to combine DF-THC with sum of square spectrum amplification, how does the problem scale for various utility scale problems. So roughly speaking, just by making a plot, the Toffoli count is n squared, lambda, gap, and lambda effective, and all scale in ways that, if you were to plot here, kind of seem to make a good fit. This is all empirical. It's just to give a feeling for, for a problem of a given size, what size quantum computer do you need? Any particular problem could have a special structure that makes it a lot cheaper than these results. But this here is a nice guide for executives and people who release money to eyeball. So that is it for the talk.
Yes, that's all great talk. Are there any questions? Yeah, please.
So my question is, if you consider both the complexity of classical post-processing and the quantum part, will the overall complexity be reduced through this sum square amplitude?
Yes, so earlier on in the first slide, I claimed that it would take on the order of hours to solve the problem.
Yeah.
And then later on, I showed that finding the tensor factorization takes on the order of minutes. So in terms of real world constant factors, you still get an advantage.
But this is because the clock rate of the quantum is really slow.
Yeah, this is under the assumptions of what we believe to be plausible for superconducting qubits. So in technical terms, we assume that our surface code has a 1 microsecond cycle time. We produce these Toffoli gates at the rate of maybe 25 kilohertz. At the ground level, this translates to a noise rate of 10 to the power minus 3. So if you were to have better assumptions or a different architecture, you would have to rescale these numbers accordingly.
Any insights gained in the process in terms of designing a general method for applying SOSUP to any arbitrary Hamiltonian?
So the key insight, I think, is going to be given by this nonlinear optimization. The SDP approach is the traditional way. It's what people in quantum chemistry or in condensed matter use to get good ground state lower bounds. But these traditional methods were really focused on just optimizing for the energy. For quantum algorithms, we need to optimize for more than just the energy. And the current best way we have is through this nonlinear optimization. So the main takeaway message is you need joint optimization in a few variables, not just the energy. And that's where there's a missing gap between classical work and what we need.
In theory,
yeah.
Theoretical.
Like how could you introduce these could you introduce optimization of these other parameters as something into the SDP directly? Maybe. Who knows?
You should have the answer. It's already enough.
No, actually, we don't have the answer. For the SDP, you can optimize for energy, but you can't quite optimize for lambda directly. There are ways to do it, but it's important to capture the lambda of the problem. So in this case, the lambda is going to be it's going to be these things here, these W's. That's lambda. So in the SDP, you could introduce something that kind of looks like that, like maybe the sum of squares of all entries, but it wouldn't be like the eigenvalues. So this is like the eigenvalues rather than like the Frobenius norm. So I'm sure you could make an SDP that regularizes for something, but it will not be like directly the thing that you want.
And I wonder, is this the main constraint in terms of not being able to apply it as a plug-in subroutine for QB or other quantum simulation methods? It's deterministic.
I wouldn't say that it is a stopper for any given system, condensed matter, Pauli operators. You can always run your SDP, or you could always run this optimization and just check to see if overall is lambda and beta better than the original lambda you started with. Like you could just run it and see if it works. Of course, it would be very nice if you had guarantees that you had the best possible lambda and the best possible beta. That'd be very nice. Maybe the optimal solution to this is a factor of 10 better, but we don't know.
And also, theoretical guarantees may be a bit overrated in the sense that ML works in practice without optimization works in practice without much theoretical guarantees.
Yeah, for this case, that appears to be so. We just need good solutions.
Do you think we can find some better basis rather than the poly basis? So actually, I somehow consider similarly. This was one of the biggest questions. I always feel maybe are there any better bases where we can handle like the terms are smaller and we can have better data in that sense?
The short answer is kind of. Everything in the end is still going to be poly operators, but instead of looking at a basis spanned by individual like poly operators or products of permanent operators, you can define groups of such operators. So, EPQ is an example. Instead of a linear combination over just AP sigma, AQ sigma, EPQ is a composite object that combines spin up and spin down together. So you can group things together, and maybe this grouping could give you a solution that has better get and maybe fewer terms. Like by grouping spin up and spin down to EPQ, I have the number of terms I need to represent the problem.
Maybe my final question is like, do you actually have a package which can automatically do the results estimation, or the results estimation is actually done by yourself?
Yeah, we're working on it.
I see.
Probably something in Qualtran.
Yeah,
Qualtran is Google's homebrew resource estimator. Yeah, we plan to release the code for all of this at some point.
Nice. Okay, so are there any questions? If no, maybe let's have the speaker.